Hi, everyone. Thanks for coming. It's great to see you all, and happy that you're here. Happy to teach you about the low frequency detection classification system, which is perhaps the worst name for a detection system ever. LFDCS. No one can remember those letters. So if you can't, that's okay. I'm really bad at naming things. I wrote this presentation probably 10 years ago, and it wasn't even new at that point. But so that's why I put "new" in quotes, because this is not really a new approach. Very little of what we do is new. It's usually borrowed from somewhere else and just sort of advanced upon. So this pitch tracking technique that I'm going to talk to you about, it comes from automated speech recognition. This is pre-machine learning days. It uses this technique called dynamic programming to find, to basically to do the pitch tracking process. And that's if you wanted to go find out where I got this. There are many ways to do pitch tracking. This was just the one that I used. And then the discriminative function analysis of call attributes that you'll hear a lot about is actually stuff I just stole completely from Doug Gillespie, who's like 3 doors down doing the Vanguard stuff. So discriminative function analysis is a way to classify things, and it's a really, I like it because it's really it's understandable, at least to me, and I'm gonna hopefully make it understandable to you as well. Okay, so I just had Julian update this because I just threw these slides in because I just want to give you an overview of what we're doing. So like in 2 minutes, what the heck is it that we're trying to do? Okay. So imagine you have a spectrogram of 40 seconds long, and the spectrogram goes up to 300 hertz. And in that spectrogram, in those 40 seconds, we actually have a couple of species calls. So in this spectrogram view, the lighter colors are louder sounds, darker colors are quieter sounds. And so you see two, hopefully, can you see the cursor? Great. Okay. So there's a Finwell call here, Finwell call here, there's a Finwell call here. These are two called 20 hertz pulse calls on the US East Coast. And then there's 2 Saywell down swoops. Okay. So all the LFDCS does is creates this spectrogram, conditions it for noise to make it nice and clean, and then does this pitch track. And all pitch tracking is drawing a line through each one of them. Okay? So that's what we're going to be talking about for the majority of the morning is how does this actually happen? How do we create the spectrogram? How do we condition it for noise? How do we draw a line through each one of the calls? And then the last piece is we do this discriminative function analysis to basically say what we have this line called a pitch track. How do I tie that to a particular species that makes that call? So we'll have what's called a call library that has a bunch of different shapes in it of those lines that says if it's this shape, then it's a Finwell. If it's this shape, then it's a Saywell. Okay, that's it. That's all we're doing today. We're drawing lines and we're doing discriminative function analysis. Okay? So now we'll dive into the details of that. So we'll talk about creating a spectrogram, smoothing a spectrogram, the tonal noise reduction and the broadband noise reduction. That's the conditioning the spectrogram for noise. Then we'll do pitch tracking. We'll extract attributes of the pitch track and then use discriminative function analysis to classify the pitch track. Okay? So many of you likely already have either made or work with spectrograms. I'm just going to go through the basics of spectrograms just so we're all on the same page. There are things about creating spectrograms that are not, that you might have been creating spectrograms for years in Raven that you might not know what's going on in the background. And so I'm just going to run you through what is a spectrogram and how do you create one. And hopefully you'll at least learn one thing that's new that you haven't seen before. So creating a spectrogram means taking audio, which is variations in pressure over time, You're very familiar with audio because you have 2 ears and you process audio all the time. So there are pressure fluctuations going on in your eardrum that your brain basically interprets as audio. We're going to take those same pressure fluctuations just measured by a hydrophone, not your eardrum, and we're going to put them into a spectrogram. The reason we use spectrograms is it makes audio visual, and we're very visual creatures. And so visualizing sound is a much better way for us to analyze it and interpret it and understand it than it is just listening to it over and over again. Although we're good at listening to things, spectrograms really, really help. So how do we go from audio to a spectrogram? Okay, the trick that we use is the Fourier transform, and we use the Fourier transform as a way to translate things in the time domain to the frequency domain. Time domain is these pressure variations are varying over time, but we want to know something about the frequency distribution of those variations. In other words, is it really high-pitched sound? Is it really low-pitched sound? Is it some combination of the two? The Fourier transform is this magical thing that allows us to translate from the time domain to the frequency domain. So if I have in this case, a frame, so let's say you take 512 samples of audio, you can run this through the Fourier transform to create what's called a power spectrum. That's what's on the bottom right. And that power spectrum, you notice that the x-axis goes from time to frequency. And we go from amplitude to, in this case, power. And so we can look at the frequency, frequencies at which there's a lot of energy, a lot of amplitude, a lot of loudness over that frame, over that, say, 512 samples of audio. Okay? The fast Fourier transform is just a computational trick to make the Fourier transform run really fast on a computer. You can run a Fourier transform or a fast Fourier transform, and they both come out with the same answer. The Fourier transform typically is very slow to do computationally. The fast Fourier transform employs some computational tricks to make it really fast. So you'll hear Fourier transform and you'll hear fast Fourier transform. They both do the same thing. Okay, one's just quick at it. Okay. First, to create a spectrogram, we turn that spectrum on its side and represent the power by just intensity of either color or black and white. So the spectrogram I showed you before with loud sounds are white and quiet sounds are dark, that's low power and high power, just represented in that strip. And then we move the frame along, and we do another FFT, and we stick that in the spectrogram right next to it. And we just keep doing that over and over and over again to create the spectrogram. So you'll hear this term frame size. That's how many samples we're going to put into our Fourier transform or fast Fourier transform. And you'll hear overlap. Overlap is how many samples are in common between one frame and the next frame. Sometimes you have no overlap. Sometimes you have a great deal of overlap. And there are reasons for overlapping or not overlapping, which I won't get into. Okay, so that's how you make a spectrogram. Spectrograms always have some sort of frequency resolution. I think of spectrograms as this giant, like, two-dimensional table. And so there's frequency resolution and there's temporal time resolution. Okay, and those are important things to consider in relation to the signals that you're trying to represent. These are the only equations I'm going to show all day, I'm pretty sure. And these are the handiest, to me, I come back to these equations a lot for how to figure out what the temporal and frequency resolution of my spectrogram is if I know the frame size and the overlap and the sampling rate of the audio. Okay? This is important because if I'm, say, for instance, I want to look at sei whales, and sei whales make sounds from like 30 to 80 hertz, and I'm using, you know, I'm sampling I make a spectrogram that has a frequency resolution of like 15 hertz. I'm never going to see that sei whale call because my spectrogram is just going to be too coarse. Creating spectrograms is part science and part art. If you can, I always think if you can see signals in the spectrogram, and I'll go back to this, you can see them, then the computer's got a half a chance of actually figuring out that there's a call there. If you can't see a call there, it's going to be really hard for a computer to pick out the call. So, and it doesn't matter at all what detection system you use, if it's LFDCS or machine learning or whatever. If you can't figure it out, it's a tall order to ask the computer to figure it out. Okay? The last thing I'll say about this, I'll just run through an example here, but the fast Fourier transform works quickly if you have frame sizes that are a power of 2. If you don't have a power of 2, if you pick something weird like 130, it'll do it. It'll just take a lot longer than if you had made it the frame size 120. So you'll often see powers of 2 when making for frame sizes for spectrograms, and that's why. It's just to make it run faster. Okay, let's smooth the spectrogram. Great. So now you have your spectrogram, and all we want to do is kind of smooth over the rough edges in it. And all we're going to do for this is averaging. So imagine you have those letters are the individual spectrum values in each one of the frequency and time bins in your spectrogram, and we want to transition over to a smooth spectrogram. We're just going to use what's called a smoothing kernel, which is just a fancy way of saying we're going to do a weighted average of the values in the red box there. And so this smoothing kernel just has it focused. I can't reach that high, so it basically says smooth things sort of towards the center. So weigh the center of this smoothing box heavily, and weigh the things that are outside less heavily. And so if you have that smoothing kernel and you what's called pass it over your spectrogram, you're basically just creating a weighted average. So A times 1 plus D times 2 times G plus times 1, and so on, and divide it all by the sum of the smoothing kernel. And that gives you one value, and you're going to stick the value into the smooth spectrogram, basically in the middle of this box. Okay? And then you can just walk this along. There's the next 9 values, and then the next 9 values. And so you walk that along for across basically the entire box, and that gives you one version of a smooth spectrogram. That's how the LFDCS does it. Okay, tonal noise. Tonal noise is something that we all unfortunately have to deal with. You're seeing a tonal noise generator pass underneath here outside. It's very perfect that we're here. That, if we had a hydrophone in the water, you'd see those horizontal lines. Ships typically make these horizontal lines at low frequencies. And we need to deal with that. If you're trying to draw lines through things that have high amplitude, if you don't get rid of those lines in that spectrogram, you're going to draw lines through all the tonal noise. And so we'd like to get rid of them. We do that. We want to account for them. We don't exactly get rid of them. We do that through a process called equalization. So to equalize a spectrogram, you'll do the following. So, okay, we're just going to average again. So don't freak out. We're just going to average stuff, and we're going to average over some time constant, some period of time. So in this case, we've smoothed the spectrogram. Now we're going to equalize it. So the smooth spectrogram we'll call S. And for one row in one frequency bin, we've got all these numbers A through O in time. And if we just average them up, we get a mean, that's beta. And so if I take the smooth spectrogram and, if I take the value of the spectrogram at the end of the averaging interval, subtract the mean and put it here, that's the equalized value. So you can imagine that as you walk along, you're averaging those that line, and you're getting a high amplitude. You subtract it from a high amplitude, and that gets you to 0. And so what that should do is basically zero out anything that's continuously loud in one frequency band. So we do that for the red line. We do it for the orange, the green row, and so on all the way through. And so then we get an equalized spectrogram. That's actually not how it's done in the LFDCS. I'm going to tell you about a technique that does the exact same thing, but does it in a much more computationally efficient way. But it's the exact same thing. So if you just want to just tune out for a little while, that's fine. All we're going to be doing is this averaging, but we use what's called an exponentially weighted running mean. It's a way to sort of keep track of the average as you go along without having to constantly look back and average up a whole bunch of numbers. So it just runs faster, but does the exact same thing. So we start out with our smooth spectrogram, we compute the mean, and we end up with an equalized spectrogram. And this is the equation we use for this exponentially weighted mean. You can go to Wikipedia and look up exponentially weighted mean, and it'll tell you all the bazillion applications in which it's used. The thing that's important is this epsilon, which is essentially derived from t, which is a time constant. This is important in the LFDCS. So this basically says if you set that time constant to, say, 60 seconds, you can calculate epsilon, and then you can use epsilon in this equation to come up with your mean. What that means is how far back in time am I going to look at to average? And that becomes important based on the nature of the tonal noise that you encounter. In most applications, you don't have to worry about this, but there are some cases where tonal noise might be intermittent, and you want to deal with it in a way that's different than you would, say, for long duration shift noise. So just keep it in mind that this is tunable for you as an LFDCS user. You can tune this, how to do this equalization. Okay? Okay, so this is what the result of equalization is. So we go from the spectrogram at the top, which is a smooth spectrogram, and we go to the equalized spectrogram. And you notice that those horizontal lines are just now removed. Ish. I say they're removed ish because you can kind of see there's still a line there, but it's much lower amplitude now. And so it's hopefully not going to botch up the pitch tracking algorithm too much. Okay? And importantly, our spectrograms are always in this very difficult to get your brain around unit called decibels. We can have a whole other conversation if you want during the break or lunch if you want to understand decibels. I'm happy to explain. But once you do this equalization, you've subtracted something away from the decibels of your power spectrum. And so now it's helpful to keep in mind that once you've equalized, the units are decibels, but relative to background. So now you have a way of sort of assessing signal to noise ratio, if that's something that rings a bell to you, if you understand what that is. You're basically saying, how loud is this signal relative to the background noise? Okay. All right, broadband noise reduction. I'm going to go through this very quickly. Basically, it's a way if there are vertical stripes in your spectrogram. This is a way, although it's not a very clever way to get rid of those problems. So let's say you have a spectrogram like this. Like, let's say you have audio, and every once in a while, there's an impulsive noise like that. And that's really annoying for a pitch tracking algorithm to deal with, because you get this broadband bang, and this happens like if you have a moored recorder, and there's like chains clanking, there's any million fish runs into your hydrophone, who knows? There's a million things that can cause a broadband noise like that. So we have to try to get rid of that. So I thought a lot about this because I use gliders like Celine, and they make clicking noises all the time that we have to account for. So imagine you have a spectrogram like this that has that red sort of broadband impulsive noise, and then this weird green one that's sort of broken up a little bit. It's not exactly completely broadband. And so I do a bunch of, again, this isn't very terribly clever, but basically isolate all cells in the spectrogram that are above some dB level relative to background. So that's, and you get to set this in the LFDCS if you want. Anything that's over this threshold, we're going to flag. And then we're going to see how vertical these things are by looking at how contiguous these values are that are over this threshold. And if they're contiguous enough to be, if there's enough samples that are over some other threshold, you would say that's a broadband noise segment. And then you add up all the segments and you say if they're over some threshold, you say, I think there's a broadband signal present in this one spectrogram time slice. Okay? Then you look across time and say if the duration of this broadband sound is greater than some threshold, yet another threshold, then you blank the broadband sound in the spectrogram. So you have control over all of these thresholds if you want to play with them. This blanking just means I'm going to set them all to 0. Remember, 0 in this case means 0 relative to background. So you're basically saying that this sound just doesn't exist. You take it out of the spectrogram. Okay? Any questions on that? Everything I just talked about is the conditioning the spectrogram, getting it ready for pitch track.
So if you happen to have one fin whale call with a tonal sound and like broadband sound, you will lose it, right?
You can lose things by if they're corrupted by broadband noise, for sure. You could also have an instance where if the tonal noise of a ship is overlapping like a fin whale 20 hertz call, you could potentially lose that call. But remember that equalization is taking away it's doing a long-term average, but the fin whale 20 hertz pulse is only like a second long. And so that fin whale 20 hertz pulse will probably survive that averaging out. So it will be.
If it's at the same moment of the whale call, you have
a broadband noise, yes, that'll
be a thrust basically on your call.
Yeah,
that'll
be a problem. For sure. Yeah. That's why you try very hard to do things like you try to quiet your platform so that you don't have issues like that. A lot of these broadband noises come from the platform itself, so we call that platform noise. So it could be something's bumping into the mooring. You have a moored hydrophone and something right next to it. You might have a shackle that's just going tick, tick, tick. That's the kind of thing that you have control of. Yes, it's going to be a mess for your detector, but you have control over that. You could make it such that that shackle doesn't move anymore, or surround it with tubing so that it doesn't, even if it moves, it doesn't make noise. We do a lot of that kind of work with all of our platforms to try to make them as quiet as humanly possible, so that both you as a human detector and computer doing the detection process just makes it a lot easier because you have cleaner audio without a lot of noise.
I would say another perk of it is you can see like periods of data. So if a fin whale is pulsing multiple times, it might miss one if there just happens to be an overlap, but you'll be able to see the context of multiple pulses, and we can usually catch them that way. It won't just give you like one little clip of it.
That's the joy of fin and humpback whales, is they give you many,
Yeah.
many chances to detect them. So you can actually have a really crappy detector and do a fine job on an animal that vocalizes a lot. It gives you lots of chances. Okay, any other questions? Okay. So let's get into the pitch tracking stuff. I'm not going to get into tremendous detail. I'm certainly not going to go into mathematics. You guys have access to the paper if you want to look at the math of it. You're welcome to. I'm happy to answer questions if I can remember the math of it. But I'll just tell you the sort of the functionally how it works. And this will be a bit like you ever see those sing-alongs where the bouncing ball like tells you what lyric you should be singing? So you're just going to follow the yellow dot here. So the way the algorithm works essentially is we walk through the spectrogram. Basically, we're going to go up, and then once we get to the top of the spectrogram, we'll move over one time step, and then start from the bottom and go up. So here we are, and all we're doing is looking for any spectrogram cell that's has an equalized amplitude above this alpha PT. Again, you have control over this alpha PT if you want. It's just saying, is there a loud sound here? And loud means any amplitude over alpha PT. Okay. So in this cell, there is not a sound that the spectrum value there is not greater than alpha PT. Great. So we'll move on. This one, no. This one, no. This one, yes. And as soon as you get something that's over alpha PT, great, I'll try to pitch track this thing, whatever I'm in. Probably the majority of the time, you're not actually in any kind of coherent tonal sound. It'll start pitch tracking, and then it'll immediately stop and say there's nothing here. But if there is something there, you'll be able to pitch track it. Okay. So once it does that, it'll go through the pitch tracking algorithm, and it will identify the time frequency position of that traces that tonal call. Okay, and this is the drawing a line through the spectrogram. All right. So what this does then is once you have this pitch track, you have a line. And that line is a compact representation of the sound that's represented in the spectrogram that was derived from the original audio. And once you have the line, there's lots of things you can do with just that line. You can characterize the shape of that tonal sound just using this line. You don't need the spectrogram anymore. And so from here on out, we're not going to talk about the spectrogram anymore once we have this pitch tracking here. That's handy both for the desktop LFDCS, because now we're just going to do discriminant function analysis based on attributes of this line. And in the real-time system, we send these lines home and put them on what looks like a spectrogram, but there's no spectrogram there. It's just a black background. And we have analysts determine what the line is, what the species is. So the human goes through sort of a classification process of their own using their own computer, and the LFDCS is taking a guess too.
Is there a huge fundamental difference between these and like the whistle and moan detector and
No.
Vanguard? It's just, is it just different math happening, or
It's different math. The math, the underlying math is different. I've never actually looked at what Doug is using, but there's a billion ways you can do this.
But
the idea,
linking times where you have these peaks. I think he
yes.
more draws.
The idea is
he captures all of it. It's not one line. He doesn't take one point. I think you get multiple. It can be fatter, if that makes sense.
I think Doug's original work was to sort of draw not a circle, but it would the line would sort of go
around. Yeah.
Around. It would go above, and then it would come back.
Mm-hmm.
and it would sort of make a closed polygon around the sound. And in this case, we're just making one.
Okay.
Yeah, lots of ways to do this, but the idea is the same. You have some vector representation of the sound, and then you say something about the shape of that thing, that vector, and then those shape attributes are what you insert into your discriminant function analysis.
Yes. If you split the frequency band in more beams, you would have a more smooth.
Potentially, yes. You want to play with the frequency resolution such that that these lines represent the tonal calls well. There are limits to that, both in how high a resolution and how low a resolution you can use. So, but yes, if you decreased or increase your frequency resolution, you would have more points on this to potentially. You just have to ask yourself, is there more information? Am I adding more information with those more points? Or am I just adding more points and I'm not really getting anything out of it? You'll see as we extract attributes, you sort of are not limited. You can put more points in there, but the attributes will come out to be the same. So you might not be adding anything, like any new information to the system by adding more points. Okay? Great. So once you've identified that there's a pitch track there, you go through the discriminant function analysis to classify it, which we'll talk about in a second. But when you're done with all of that, we want to basically blank out this sound so that we don't keep encountering it and keep tracking the same sound over and over and over again. Because remember, we're doing the little yellow dot, and the yellow dot ended here. The yellow dot's still it's gonna go all the way up here, it's gonna start back here, and once it hits here, if we haven't done this blanking, it'll pitch track this thing all over again. And it'll pitch track it when the yellow dot hits here, and here, and here, and here, and here, and so on. So blanking just says, go above and below a little bit, and to the left and to the right of this, and just insert zeros. And then it's blanked, and the pitch tracking algorithm will never find it again. Yeah.
In terms of computational time to do the tracking, if our database is a sampling frequency of 48 kilohertz, and we are looking to say whales, for example. It would be advisable to downsampling.
Absolutely. Okay. Yep. And the LFDCS allows you to resample your audio for exactly that problem or issue. Okay. Remember in the equations I showed you, the frequency resolution as well as the temporal resolution have sampling rate in the equations. And so you have to pay a lot of attention to what sampling rate you're using to make your spectrogram. Okay, so once we found our pitch track, great, we're done. Then the yellow, we've blanked the pitch track, and then we just keep going on with the yellow ball, and, just checking cell after cell after cell. And this, because we blanked it, we just will never find this this tonal call again. Okay, so here's what the whole thing looks like. So at the top is the original spectrogram. We smooth it. The lower left-hand corner is we've done the equalization. The upper right-hand corner is we've pitch tracked this. And then the lower right-hand corner is we've blanked it. And you can, if you look hard, you can see that these are all the same value. Let's see here. Those are all the same value. It's 0. So, and that's it. You can see that the pitch track successfully jumped over the gap that the equalization used. It's not the prettiest of pitch tracks, but it'll probably do for the attribute extraction, and it'll probably classify just fine. And this is a good example of why pitch tracks that you see in real time sometimes look crappy. It's because there's been this equalization that and that kind of cut holes out of the tonal calls. Okay? All right. I'll get into just very basic details about the pitch tracking algorithm. The best way that I can think of to explain it is a very old problem in computer science called the traveling salesman problem. This is the basis of the algorithm that I use, or at least this is the way I think of it working. Okay, say you're a salesman and sorry, this is very American focused, but you're in San Diego here, and you're traveling across the country, and you're going to end up in Philadelphia. Okay? And as you're going across the country, you're going to be selling whatever widgets, whatever thing that you're selling, because you're a salesman, you're selling things. Okay? And you know, if I go, for instance, to Denver, I can sell $1,700 worth of my stuff. If I go to El Paso, I can sell $400 of my stuff, and so on. So the trick is how do I get from San Diego to Philadelphia quickly, but making the most amount of money possible? So there's a million applications of this problem to all kinds of things in science, but this is in pitch tracking. How do I get from the beginning of the pitch track to the end of the pitch track while following the contour of the tonal call, where basically the amplitude of the tonal call is the dollar amounts here, right? How do I get through this tonal call but stay at the peak of the amplitude? Okay, we want to maximize revenue and we want to minimize the distance traveled or the cost. And this is exactly what we do, where the reward in pitch tracking is the amplitude of the individual spectrogram cells, and the cost is we want to be as direct as possible. We don't want these crazy jumps. Okay, I'll go through this quickly. So let's say we start pitch tracking in the middle of this Saywell downsweep. So this is a 2.5 second spectrogram. It's really fuzzy because we're really focused in. So what we do is we come up with this cost function. It basically says, if I'm stepping to the right in time, I could step to any one of these dots. And if I did that, what would be the cost of that relative to the gain that I get? So again, if I want to maximize revenue and minimize the travel costs, then the amplitude is sort of my revenue, and then I come up with a penalty. If I jump really far, if I go all the way up, my next move is all the way up to the top of the spectrogram, there'll be a big penalty for that. I've traveled a long way. But if I just went to the next cell over, if I went to this dot, there'd be virtually no penalty at all. That's the smallest distance that I can travel. And so if you match that, the penalty for jumping versus the amplitude of sticking with the highest amplitude, that would tell you that this is the next best jump. Like that's what this score is the amplitude minus the penalty. And so it would tell you the next best jump is to here. And so you jump there. And then it says, okay, if I'm going to go to the next one, what's the sort of risk versus reward? What's the benefit versus the penalty? And you just keep doing that. You keep making this function, and it tells you basically where to go next. And it essentially traces out the call. When you get to the end of the call, you turn around and you go all the way back. So we always forward pitch track and then backward pitch track. And then we take the backward pitch track as the pitch track that we'll move forward with. We do that because we don't know where we will have landed at the beginning. So when you start pitch tracking, there's no guarantee you're at the very beginning of the call. And so the back pitch track gets you that little tail end. Yes.
Is that because your threshold, your initial yellow dot threshold is higher than, this allows you to be more sensitive once you've got, okay.
Exactly right. So we might have started pitch tracking, here. And in which case, if we forward pitch track and just say, okay, we're done, we would have missed this initial bit of the call.
Yep. Every time you compute a score, you compute it for the whole matrix.
Yes.
Every step.
For the next step.
Yeah, but
yes.
So it's
for the
it's
entire
still one matrix every step. So do you reduce the size of the matrix you compute the score for, or do you use the full spectrogram?
That's a great question.
Because
I can't remember. It would make sense to I can't honestly remember. I'd have to look at the code for that to answer that question. Because the tricky thing here, Quentin, is that you have to if this call was really, humpback whales make these really fast whoop sweeps, that if that change in frequency happens at a very short time scale relative to the time step, then sometimes you will jump a long way, and it's totally legitimate to do that. And so I suspect my code doesn't cut you off as to how far you can jump by only looking like in a neighborhood. It probably looks over the entire. It calculates that function over the entire spectrum.
But like, is it a 2D matrix or like just one?
So all you're doing is looking at the next. All you're doing. This function is just where should I jump next in the next time step, and then you calculate this function again and say, okay, where should I jump in the next time step? Okay, and this helps you decide where to jump next. Okay. All right. So great. Now we have a pitch track. There are 3 parameters that you have control over that govern how the pitch tracking algorithm works. At alpha PT, when should I start pitch tracking? When do if I get a cell in the spectrogram that's over alpha PT, then I'll start pitch tracking. The weight, which is how much penalty do I assign if I jump a certain amount? That if you increase that a lot, that moves the algorithm towards making much flatter pitch tracks than kind of steep pitch tracks. And then the gradient threshold is something that that the algorithm uses to decide when to stop pitch tracking. So you can fool around with all of these and see. When I was first starting doing this, I would have like a 2 or 3 minute snippet of audio that I would take a set of these 3 parameters, run it, look at it, and then say, okay, what if I change the weight? And I'd like double the weight, and then I'd run it over the exact same 3 minutes of audio, and then I'd look to see, okay, what was the result of changing that? And fooling around with these 3 parameters in that way to try to get it so that the pitch tracks sort of represented what my conception of what was going on in that spectrum. Okay. That's the art versus science part of this, which as scientists it makes us like feel very uncomfortable. But once you get it tuned in, you'll have that process gives you helps build up your confidence that the pitch tracking algorithm is doing what you think it should do. So it's a good exercise to go through. Or you can just use the values that we've used for years now. I mean, Jen's done a ton of work with the LFDCS, and we have a set that we feel pretty comfortable works with our species in the Western North Atlantic. So, and it'll probably do well for your species as well.
You've never tried like parametric optimization with like a synthetic spectrogram, for instance?
So there was a German student that tried a lot of that, just like using, basically going through that parameter space, that three-dimensional parameter space to figure out what's the best parameterization. You can do that. That's an objective way of doing it. But that, I found that to be not super helpful.
Maybe it changes for every hydrocarbon.
You can certainly overfit that kind of an approach. There's a danger of overfitting it to the exact data set that you're using, and then it's not really applicable elsewhere. And you'll find that out quickly when you apply it to an independent data set. But that is one way to try, if you want to go ahead.
But you use the same set of parameters for all your species, all your recorders, all the places? You use the same set of parameters?
Pretty much now, yeah.
I haven't touched anything in the parameter file that's of the pitch tracking version.
Yeah.
But of the parameters before, because you had other parameters for the denoising stuff. Do you touch these?
Yeah,
parameters?
no, we don't touch those. So we've used this up and down the East Coast for fin, say, blue, humpback, and right whales. We've used it off of Chile on gliders for, mostly say in blue whales. We've used it on the US West Coast for bluefin and humpback whales. We've used it on gliders in the Arctic for bowhead, ice seals, and we use the same exact parameters. So
it detects everything, and then it's the next part which classify.
yes, the classifier is the thing that you guys will probably play around with the most.
Okay.
This stuff, you can, if you want to play around with this, go for it. But we've come up with parameters that it feels like they're working for most situations. Okay.
Just as an example, I would say there are calls I see in LFDCS going through that when I look at Raven or another program, I don't see them. So I think it does a really good job pulling out calls and negating the background noise.
Human experience.
Yeah.
Not standard parametric optimization in sense.
So Jen has written a couple of papers where she's analyzed over 35,000 days of data with the LFDCS. So she has that human experience.
A big fan.
Yeah. But do you sometimes have signals that are not from whales or marine
Sure.
mammals?
Oh yeah.
But then, what does it like in the classifier? It's just they get thrown out because they are not.
Depends on your classifier.
Okay.
So air gun noises are readily pitch trackable, and depending on your distance to the air gun, the type of air gun, they can look all kinds of different ways. And I know our colleagues in Canada, like Jack Lawson's group, has had a lot of trouble with that. And so he's been trying to build classifiers to try to separate the air gun noise from the binging noises. Yeah. But that's something you would do on the classification side, not on the pitch tracking side. Okay. Okay. This, I think, is the much more fun part of this, is the last two, because this is where you can apply it to your own stuff. The rest of it is kind of, can be treated as sort of baked in. Okay, so once we have the pitch track, we're going to extract attributes of the line. So we have a line, we're just trying to describe its shape. Okay, so we pull off seven attributes. How long it is, the duration, the frequency times slope, the the average frequency, the frequency range, what band it's over. And then there's this sort of shape thing that I threw in after we wrote the original paper, because we were getting bowhead whale calls that were like shaped like a U. And so getting the slope of the first, second, and third thirds of the call became attributes to deal with that shape distance. Okay. So we have this complicated spectrogram with all kinds of things going on in it. We've boiled it down to, we've picked the tonal noise and we've just drawn a line, and then we've gone from that line to 7 numbers. And the 7 numbers is what we're going to use from here on out for the classification process. Okay, I just said that. And I will say the attribute extraction, if you look at the equations in the paper, look kind of torturous. It's just we amplitude weight things, and so we want the attributes to sort of reflect to be influenced by the amplitudes, such that we don't have attributes that get crazy because the pitch track is pitch track some really quiet part of the call where the pitch tracking gets really hard, and so we can have lots of errors in the pitch tracks when things are quiet. And so this sort of tries to focus mostly on the loudest part of the call, where we're most confident that the pitch track is capturing the frequency and amplitude modulation. Okay, here we go, discriminant function analysis. So our goal is to compare those 7 numbers that we just got off this unknown call, this total call that we pitch tracked, we've gotten the 7 attributes. We want to say, okay, who made this call? So how do we do that? So we're going to build a call library that has call types. And so a call type could be, for instance, the Finwell 20 hertz pulse call. Some species make variations in their calls. Right whales are a good example, where a right whale up call, not every right whale up call is the same as every other right whale up call. And so we'll make sort of families of right whale up calls. Some are steeper, some are less steep, some have like this little hook at the beginning. We'll make call types for each one of those. So a call type doesn't necessarily mean a species, that there's one call type per species. There might be multiple call types per species, even multiple call types for the same call. But we're going to make these call types. And then we're going to, so imagine the call types just describe what that line should look like for this particular call type, this particular species, okay? And so if we get, prior to trying to figure out what this new call is, if we've gone through a whole bunch of data and we figured out this is what this line should look like by collecting like 200 Finwell calls and pitch tracking them, and then extracting attributes. And so we have 200 sets of attributes for what we know are Finwell calls. So I'll take those 200 values and summarize them. And then when I get a new call, I can compare it to this summary. That process is called discriminant function analysis. A distribution of those 200 Finwell exemplars is going to have this multivariate distribution. And we summarize that multivariate distribution using something called a variance-covariance matrix, which I'll describe in just a second. And discriminant function analysis just says, given a new set of 7 values, I'm going to compare it to that variance-covariance matrix for every single call type, and I'll tell you which one it matches best. So it's just a matching game. That's all. Discriminant function analysis is just like a matching game. Who does this line match with? One really nice thing about discriminant function analysis is this last point, is that it will tell you this new call doesn't match anything, doesn't match any of the call types in your call library. And that's really useful, because you might get tonal calls that either are a new call that you've never experienced before, or that's just you haven't stuck into your call library yet, or there's noise, and it'll say, I don't know what this is. And that's really handy. Okay. So let's imagine, I've been talking about the fact that we have 7 attributes. I can't, at least in my mind, visualize a 7-dimensional space. So let's say we had a call library with just 2 attributes, because I can visualize that. Attribute 1 will be on the x-axis, attribute 2 will be on the y-axis. One way of thinking about this is with people. People have a height and they have a weight. Let's say you had those 2 attributes for people. And maybe you had men as one group and women as another group. I can tell I'm going in a very bad direction. Super off the cuff.
Dutch people versus.
I was also nervous about doing that, but yes, okay, we can do like the Dutch and the Belgians, right? So that's true. The Dutch are very tall people. So one group is the Dutch and one group is the Belgians, and you can maybe separate them by their height and weight. Okay, just the same way. For some calls, they might have a higher average frequency and a lower slope. I don't know. Or let's do it this way. They might be longer calls and higher frequency versus shorter calls and lower frequency. Okay. So we're just going to use 2 attributes for all of these examples, just to get your brain around what discriminant function analysis does. Okay. So we have these 2 attributes, and we have these 2 call types, the red call type and the green call type, okay? Each one of the dots here represents an exemplar. So you've gone through your audio, some archived audio, and you said, I want to build a call type for Finwell 20 hertz pulses and Saywell downswoops. So that's 2 call types, and you're going to do it by just two attributes, okay? So I picked out like 100 Saywell calls, and I picked out 100 Finwell calls, and I've measured attribute 1 and attribute 2 for both of those call types, and I just plot them. Okay, so the green might be Finwell calls, and the red might be Saywell calls. Okay, so again, we have this in the LFDCS, only it's in 7 attributes. Okay, so if you get a new call and you measure its attributes and you plot them in this space, that new call groups with all of the red dots. And so you say, must be a red. If you get a new call and it groups with the green, you'd say, that's a green call type. And if you get something in the middle, you want to be able to identify that it really doesn't match either one. Okay? That's it. Now you know how discriminant function analysis works. Because it just does all the math for you to tell you exactly what I just told you. It groups with the red, it groups with the green, or it doesn't group with anyone. Okay, so let's talk about what discriminant function analysis is going to give you some numbers to tell you how well this new call matches with a call type. And it does that using a very difficult to pronounce name called the Mahalanobis distance. And so I'm just going to talk about Mahalanobis distance and what does it actually measure. Again, all it's going to do is going to tell you how well a new call type groups with, say, for instance, these red dots. So imagine if we just measured one attribute. Let's not look at this. You had one attribute and you just had like a histogram for that, right? That histogram for that attribute, again, Dutch people, their height. So you get 100 Dutch people, you measure their height. You look at that in a histogram. That histogram has a mean, if it's normally distributed, which it probably is, has a mean and it has a standard deviation, right? It has a mean and some variation about that mean, okay? So this, remember I talked about the variance covariance matrix, which is a fancy way of saying what's the variation in attribute 1, what's the variation in attribute 2, and how are they correlated to one another. If I have length, height, and weight for people, those two things are generally correlated with one another. So if I plot them up together, it just isn't like a scatter shot. It has some tilt to it, and that describes the correlation between the two. So variation is the standard deviation of attribute 1 to attribute 2, and the covariance is the correlation, variance covariance matrix. It just describes basically the shape of the scatter of those dots. Okay? Mahalanobis distance is a way to say, if I have a point, how far away from the middle of this cluster is the point given this variance covariance, the variance and covariance. So here's an example. The lower dot, let's just talk about this dot. This dot, if I measure the Euclidean distance, meaning what's just the length of this line, given the attribute 1, the x and y axis here. And that distance in that space is 80. But the Mahalanobis distance is way outside this cluster. The Mahalanobis distance is I'm just going to tell you, it's fairly big. It's 3.67. Whereas this dot, which is the same distance away as this dot, so this is still 80 units, it has a much different Mahalanobis distance. It's much smaller. So the closer you are let's see this, the closer, the more inside of this oval you are, the lower your Mahalanobis distance is going to be. That doesn't apply necessarily to this just straight line distance. Here's another example. So these two dots have the same Mahalanobis distance. They're the same, they're on this oval, which describes the variance covariance structure. Describes sort of the perimeter, almost the perimeter of this cloud of dots. Has the same Mahalanobis distance, but very different Euclidean distances. Okay, so think of Mahalanobis distance as just how close am I to the mean of this cluster, which is this middle dot. How close am I to the mean, given this variance covariance structure? Another way of thinking of it is how into this cloud of dots am I? Right? Big Mahalanobis distance, you're outside of the cloud. Small Mahalanobis distance, you're in the cloud. All right, so let's have a call library with 2 attributes as before, but let's put a bunch of call types. So now we have 4 call types in here. There's this thing that's really handy to keep in mind. We don't use this practically, but it's a great way to visualize it. This thing called a territory map. That simply says, if my new call shows up in the red cluster's territory, I'm going to classify it as a red call. Okay? So if we have a new call that's in this case with the green, the discriminant function analysis says if it's anywhere within this shade of gray, I'm going to classify it as green. Okay? Okay. So these are the numbers that discriminant function analysis gives back to you. The Mahalanobis distance, and then there's this thing called the relative posterior probability of group membership. Let's put that aside for right now. So you can see that the Mahalanobis distance for green, 1.5, means how close is this dot to the center of the green cloud? Close, really close. The red number, 12.9 for the red dot, is how close is my new call to the center of the red cluster? Really far, right? From the blue, 14.5, really far. From the light blue, 17.4, really far. Great. You could just classify based on the Mahalanobis distance, but I'm going to show you an example where this gets a little tricky to do. So what we do is look at the relative posterior probability of group membership. which tells you how sure is discriminant function analysis that this call really belongs to this, to the green cluster, or to any of the clusters. It's calculated for each of the clusters. So in this case, this call is really in the heart of the green cluster, right? Mahalanobis distance is low and it's very far from the other ones. And so discriminant function analysis gives you back the posterior probability of being part of the green group as 1. I'm really sure it's a green. And for the other ones, it's really sure that it's not blue, red, or light blue. Okay? All right, let's do a slightly more complicated version of this. Let's say you had a group that was 2 groups that were quite close together in attributes, so the red and the yellow. A great example of this is up calls for right whales and humpback whales. This is very much, we encountered this situation a lot in the western North Atlantic with right and humpback whales when they're together. Here's what the territory map looks like. So again, if you're in one territory, you'll be classified as that color. Okay, let's go through some examples. Here's a new call. It's really close to the border. So now the Mahalanobis distance between the new call and the centroid, the middle of the yellow cluster, is 1.3, and the distance to the middle of the red cluster is 1.8. And you notice the posterior probabilities are not clear at all. It's saying, yeah, this is in the yellow cluster, but man, I'm not so sure. It's only 72% chance that it's actually a yellow versus a almost 3% chance that it's, 30% chance that it's a red. So this is a case where you'd be like, maybe it's not so clear what this case is. But if we, here's an even worse case. It's right on the line, right? The Mahalanobis distance is almost equidistant between the 2 centroids, and the discriminant function analysis for the posterior probability there is saying I'm not really confident in either. But if you moved it into the red, it's fine, right? The posterior probability goes up for red, and the Mahalanobis distance goes down. And so you'd be a lot more confident in this. And this is where it gets helpful. The discriminant function analysis is really helpful in that it will tell you if it has no idea what this call is. So here's a new call that's way out. It's in the red territory. So that territory map, that dark gray, it's in the dark gray, so it's going to classify it as a red call. But it's going, so the discriminant function analysis always classifies things. But it's up to you to decide, is this really a red call or not? And in this case, so you see the posterior probability is really, really high. It's like, I know of all these call types, I'm most confident that this is a red. But if you look at the Mahalanobis distance, it's really large. And so this is a call that you would say, this is something that's not represented by my call types. Okay? I'll give you one last, no, I won't give you one last. So here's an example. You've already seen this example of the say-well down sweeps and the fin whale calls. But now instead of circling them, we can actually put the classification information on here. And so let's say I have a call type here for 1 for say-well down sweeps, 2 for an unknown call, and 3 and 51 for fin whale 20 hertz calls. So now, not only do I get the pitch track, but I get the classification information as well. Here's another example of 2 say-well down sweeps, and over top at a higher frequency, there's 2 right whale moans. And so same thing, we can, and that's kind of not a very pretty spectrogram either. There's total noise in there, but it pitch tracks just fine. And now we get classification information as well as the pitch tracks. Okay. Another example of some up calls and a right whale moan, and we get classification information. All right, I think I'm, close to done. Well, let me stop there and see if there are any questions on any of this stuff.
Generally, what Mahalanobis distance do you accept?
So there is, we typically use, depends on your purposes. 3 is a decent number to use. That's what Jen used for her work. So,
Except for blue whales. Yeah.
what's that?
Except for blue whales.
So Mahalanobis distance has a theoretical distribution. If your call types are multivariate normal, meaning that oval that I put on here is a good representation of the scatter of all those exemplars. If that assumption is met, then the Mahalanobis distance will have a known distribution, meaning at Mahalanobis distance 3, I'm trying to remember now, you can have, I think that sets, you could have 33% of your exemplars basically would be over Mahalanobis distance of 3. Meaning, if you use Mahalanobis distance of 3 as a cutoff, you're being fairly conservative. Meaning you're going to throw out some actual calls, but it's going to reduce the amount of calls overall that you're going to have to go through. Mm-hmm. So again, this has a lot to do with what your purposes are for using a detector. One way of using a detector is to just run the detector, take the detector output, and publish on it. Never look ever at the calls. Just trust the detector output. I would never ever suggest that you do that ever. But if you wanted to do that, you could. If you did that, you would want to be really, really sure that you're not getting false detections. And one way to make sure that you're not getting false detections is to lower your Mahalanobis distance. If you lower your Mahalanobis distance, you're basically saying, only give me calls that really, really, really match my call types. Okay. Another way of doing detection is to have the detector go through all the calls, and then you, as a human, look at every single detected call that comes out of that process, and basically manually throw away ones that are false detections. That's a way of driving your false detection rate down, which is great. Then you can go publish on that, and you've got something that's reasonably believable. But when you do that, you have to be really careful that your misdetection rate isn't also really, really big. So if you don't want to miss things, you would make your Mahalanobis distance bigger. You would say, give me calls that maybe don't match perfectly with my call types. Some of them are a lot of them are going to be false detections, but I'll be able to catch all the sort of marginal ones that really are real calls, but they maybe didn't pitch track well or whatever. So that's another way to go. So the Mahalanobis distance threshold that you pick really depends on how are you going to use this detector. And that applies to any detection process. Is you're going to have this threshold at which you're balancing misdetections, false detections, as well as the amount of work that needs to be done. Like you could make your Mahalanobis distance 10, right? And you probably have a really low misdetection rate, but you're going to have to go through like 3 million calls manually, going through a bazillion false detections because you set your Mahalanobis distance so large. And so this choice of the threshold is always this balance between what your goals are for the analysis and misdetection, false detection, and the number of false detections that you produce. So when people say, what Mahalanobis distance should I use? The next question is always, well, what are you trying to do? What's the goal of your detection
Yeah, because my problem, I took over the project from another person, and we work in the Caribbean, and I don't really have knowledge myself of what is there, and I don't have a call library.
Mhm.
And I think the value that you get in Mahalanobis distance is also dependent on your call library.
Right.
So you need
Yes.
to build like a quite trustable call library
Yes,
to have Mahalanobis distance that you can trust.
yes. So you would have to build a call library and then evaluate. You have to use a data set to say, well, how good is this? So again, that's not specific to LFDCS. That's any
Yeah.
detection process. You have to make some. You have to evaluate. So you'd evaluate it for false detection rate. You'd evaluate it for misdetection rate. The nice thing is so what people often do is they'll run their detector, and they'll also go through that same data manually, and they'll figure out where are all the real calls. And then once you have that manual analysis along with the output of the LFDCS, for instance, the LFDCS gives you, for every pitch track, it just tells you, here's what the Mahalanobis distance is for this relative to this call time. Then you can do an analysis where you look at different thresholds for the Mahalanobis distance and what false and misdetection rates do you get if you used that Mahalanobis distance threshold. And so you can go through and basically figure out what's the right Mahalanobis distance if I wanted to have this false detection rate and this misdetection rate. And that's a way to help you choose what the threshold should be given what your goals are for using that detector.
Okay.
That make sense?
Yeah.
Yeah.
To compute the territory map, do you use the k-mean? Other?
Territory map, that's a great question. How do I compute that? That might be by brute force. It might be that I have, I make 1,000 by 1,000 grid, and for each one of those, I plug that attribute into the, I say, if I had a call at this particular location, like, you cut this up into 1,000 by 1,000 grid cells, and for each, not 1,000 by 1,000, it's too hard, 100 by 100. So you've got 100 values for attribute 1 and 100 values for attribute 2, and for each pair, you go and you say, okay, if my new call was here, it had attribute 650 and attribute 1 is 150, where would it be, what would it be classified as? I think that's how I did this territory map. It's just a visualization technique. It's just really a way to help
There's
you.
Plenty of clustering different techniques.
Sure, yes,
I don't know which one is the best.
Yeah.
You never know.
No. But discriminant function analysis is sort of taking care of the clustering for you.
Yeah.
Mark, we're about 5 minutes into the official break. I don't think
okay.
it really.
I have a few more slides. So.
Yeah, I don't think it really matters if we're totally spot on with them.
Okay.
Yeah.
All right. Do you want me to keep going, or you want to do?
Sure. If you have a few more, yeah, you just have a few
It's
more
whatever-
minutes.
yeah,
I
you
think
can
we
keep
just
going,
finish
or
it
we
up.
can start
Advantage
back
is
with this.
limitations, and then you guys are going to cover this anyways, and that's it.
Yeah, okay, yeah.
I'll do advantages and limitations,
Sure.
and then we'll
Yeah.
break. Okay. So, so nice things about the LFDCS. It's relatively insensitive to system gain, meaning it really, because you do this equalization, it's you're not. It handles different recording systems. If they have different sensitivities, it doesn't matter because you're doing all of your work on dB relative to background, and so that's nice. It's mostly insensitive to spectrogram creation parameters, meaning if you change the spectrogram slightly, it doesn't really matter. The pitch tracks will likely come out the same. And again, we're trying to, it doesn't necessarily even matter what the pitch tracks look like, it's what the attributes are. And changing the spectrogram a little bit here or there isn't going to change that very much. If you have very different spectrogram creation parameters, that will affect it, but it's insensitive to small changes. One of the nice things about this that those of us who use it like is that with one pass through the data, you can get multiple species, detections of multiple species, and that's nice. I'm sure many of you have used very species-specific detectors, and then you say, well, I want to change species, and they have to go get some other detector that uses a whole different workflow, and that can become kind of nightmarish. So this is that part of it is nice. Incorporates variability in call parameters. You saw that I had right whale moans on there. Right whale moans are difficult to detect with things like kernel spectrogram correlation methods. This whole discriminant function analysis sort of embraces variability in call parameters, and so that's a nice aspect of it. I just said that. Adding new call types is pretty trivial. I mean, I feel like if you've got a bunch of exemplars, it takes maybe a couple of hours at most to make a new call type. And then one of the things that I like is that you can share your call libraries. If you come up with a new call type, you can share it with the community. We just saw that with the folks that did the blue whale call types up in Canada. There are, of course, limitations. It requires reasonably loud calls to detect and estimate the shape of calls by pitch tracking. Spectrogram correlation, which I just mentioned, can detect calls that are much lower in amplitude, as long as they conform to the shape that you expect them to be. The LFDCS is doing two things simultaneously. It's detecting and characterizing the shape of the call at the same time. And you need some amplitude. You need some signal to noise ratio. You need some amplitude to do that. It's not useful for broadband signals. So if you thought it was going to do like click detection, it's not going to do that. Although I have a separate broadband detector, I'm not going to talk about that. It can't, like we talked about before with these humpback whale upsweeps that are really, really fast, it can't accurately track calls whose pitch changes faster than the time resolution of the spectrograms. One of the things that you have to pay attention to when you make these spectrograms is, am I going to have really rapidly changing calls that change rapidly in frequency? And then finally, if you are in an area where there's a lot of tonal calls being made simultaneously, pitch tracking becomes really, really hard. Anyone that's worked on whistles, dolphin whistles, knows this problem well. Anyone that's worked in the Arctic knows this very well. If you've got a bearded seal, like just singing its little heart out, and you've got bowheads, 50 bowheads, it's a cacophony of sound. It's very difficult to do this pitch tracking. So
I was gonna ask that, have you tried it on whistles and it just is too?
yeah, I haven't. Yes, not enough to say how well it works, but I can almost guarantee you it's not going to do what like.
It wasn't like, oh, keep exploring this. It was sort of like, yeah, it's not.
Because other people are doing it better.
Yeah.
So I haven't gone down that road. Although you'll see on Wednesday that I'm moving towards that, sort of reluctantly, but I don't think it's going to do as well as.
And there's lots of other options out there.
So that's it. That's we'll talk about the ideal programs later. All right.
Cool.
Let's do a break.